So in this next topic, we are going to talk about power screws. Power screws are those screws that are meant to actually hold load. So they're not meant to keep two surfaces together, but they're meant to actually just hold an entire load that you're applying to the structure. There are many different examples of that. You have all the examples go everywhere from aerospace engineering to shaft design to car design, uh, and civil engineering for bridges. They are all over the place, actually. And actually, you have some of these that actually used in biomedical science as well, especially for orthopedic applications. So power screws have become and they come with many different materials. You have um, carbon steel, they make titanium. They're more popular in titanium. They're very strong, but expensive. Yeah, stainless steel, and the list goes on and on and on and on and on. What you can possibly have, um, and so in every industry, when you go to, every industry has their own way of using and what they want to use and what they want to use. Okay, they have a list of database of these are the screws, the fasteners that we will be using, and you just choose from them. Here in this class, we will focus our attention to the options that you have available in your textbook. And I'm going to use a lot of complementary information as well from other places that will actually help us in this discussion. So let's begin our discussion on power screws. And this, we're going to start with the theory. And as I mentioned to you, you see a bunch of applications. They're all over the place. You have um, power screws. Actually, you can see them here across here on the engine. They hold the engines in place. You have civil engineering applications. You have, this is an example of a gas, a heavy duty gas pipe that's held together by this cylinder. And these are power screws. And then this right here is some power screws have collars, sometimes some don't have collars. There are different applications of these collars, so they have the same weight. If you think this is all having the same weight and different application, different ways, so but the analysis for the screw itself is the same. Now in this application, you could probably ignore the color. In this application, you cannot. In this application, you cannot ignore the color. The color and the screw and the system actually act all together. So there are different ways to analyze and study this problem. Okay. So depending on the case you're working on is the type of application that you will use. Now, to give some definitions on how we actually work these definitions are important in this discussion. First of all, you got three different diameters here. The major diameter typically we use a called letter D. The minor diameter is DR, is the root diameter, is the one that goes from the inner part of the thread to inner part of the thread. We call that the root. That's why it's called DR. Then the pitch diameter is mainly the mean diameter between these two diameters. And sometimes we call also this DP because it's pitch or mean. So many textbook and places you go to, they interchange this back and forth, but it really means the same. And the auto diameter is if we just take a full length right here, that's what it will give you. Okay, so another thing that you have is you got the thread angle, and most of the time this thread angle is alpha and alpha, and typical value of 2 times alpha is 60 degrees. This is very common. And if alpha is equal to 0, this is actually known as a square thread. Okay, then we would talk a little bit more about this as we move along. You have the definition of pitch. The pitch will go from one crest to another crest. And then another thing you can see here, just to give you some definitions, I already gave them in the previous slide, but maybe this is a little bit more helpful. So this is the pitch diameter that goes from here to here. Okay, this is the pitch diameter. Sometimes it's also called the mean diameter. I'm sorry. This one right here. My apologies. Goes right here in the middle. Okay, it's the mean. And we used, as I just told you, DM or DP for this. This is the root diameter or the minor diameter. Okay, so this is minor, or let me just do this. Let me call this DR, and then write DR here. This is minor, or sometimes we call this the root diameter. And then you can go from here to here. This is your D. D is known as your major diameter. And please be aware that different textbooks, different manuals have different notations. So please don't just assume that these are the only notations out there. That can vary from manual to manual, company to company as well. Another thing that you may want to consider is the type of lead, right? You got single thread lead. What you're saying is if I give one turn, one full turn, it only goes one pitch. Okay, your uh, your uh, your your nut will move only one pitch. If the lead is 2 times the pitch, when you make one turn, only one turn, you will move 2 pitches. See, it goes from one thread, it goes 2 threads. And 3 pitches is that it goes to 3 threads. Okay? So then you can call this N, in general lead is equal to N times P, where basically you're saying in one turn, this is the number of threads that are engaged. Okay, this I'm not sure if it's in your textbook, but this is very, very important. Your lead is not equal to P. Okay, many textbook or many just say L is equal to P, but they're assuming that N is equal to 1. Okay, if it doesn't say that, then if you had two times the pitch or 3 times the pitch, then it's called triple threaded, double threaded. In that particular case, then you will have those situations here. Okay, so just keep that in mind. This is given from the problem, and this is what you're really interested in. Then another thing you have is the thread sign conventions. You got different type of threads and different applications for that. One, you can use the right-hand rule. The other one, you can use the left-hand rule. This is so single start, 2 start. So basically what you're saying is you're going to move twice when you do one circle. You move twice when you do one circle. So if you look at this is 1, this is 2, this is 3. So in 3 turns, you actually move 6 threads. Here in 3 turns, you only move 3 threads. Okay, and they all go in opposite direction. Each one of them have their own purposes and applications. So some of the right-hand and left-hand rules, right-hand, left-hand threads, they look something like this, right? In this case, if you do clockwise, here if you do, you have to turn it counterclockwise for this to get engaged. This one you turn clockwise to get engaged. Especially in shaft, sometimes you use that, so that way you always keep it tight. One side will be right hand, the other one will be left hand, so that way you always keep it, you can keep your whatever you're doing, it's easy for you to tighten it up. This is an example of that. You can see that you have one power screw, but then you have one side is right-handed, the other one is left-handed. Another example of that you can also see here how this works. So the way this works is, let me change the colors here quick. So the way this works is you are really doing this in this direction. This one you're rotating in the opposite direction. And here what you do is you basically rotate everything here in this location. And as you're rotating, you are tightening this up. You rotate in the opposite direction. You loosen up both of the mating surfaces. Another applications of that you can use, and these are also known as power screws, but these are not so much. They actually work with fluid. Okay, they are meant to move fluid from one spot to another, and we mechanical engineers we design these two. These are right hand side. This is the left hand side. They all have the same purposes. They're just rotating in different direction. Okay, and so this is what that type of screw will actually do. The rotation of that direction, it just tells you it will go what direction the flow goes, right? So this is rotating in this direction, the flow is going in this one. And if it's rotating in the opposite direction, it's going in the opposite direction. So you can basically kind of understand how this works in right hand or left hand side. Okay, so one of the things that you have many different applications for different type of threads. The most popular threads I would say are these two threads right here. I'm not saying the other ones are not used, they are. But in the case of power transmission, if you think, especially if you have a jack, and let me see if I can even, if I have a jack and I got the power screw here going right in the middle, right? And this is your screw. So this is your jack, right? And then you are just going up and down direction. So everything that's holding in this particular screw, this screw is holding the whole load in here. That's what it's taking care of. In this case, since this is a power transmission, you are really transferring power, you want to use square. This has a much better engagement because then, you know, whatever goes there, it has a much better engagement there. Here, this is very good for shear applications, especially fasteners and joints, and we will talk about that as we move along. Okay, then you have many different, you can follow me. I have a handout and all this stuff is in the handout. You can download the handout as well. Then the American National Unified, we call it Unified Thread Series. So if it's a core series, this is very good for general applications, frequent disassembly when you want to assemble and assemble. It's really not good for vibration applications. Because you don't have a very good engagement. If it's a little bit loose, then or it's not fully tight, and you cannot tighten it because you want to assemble it, disassemble. In those applications, then it's not good for vibration applications. Okay, in the fine series, now in the fine series, a better adjustment, better engagement is very good for vibrations. But the extra fine series is much better for vibration. It's a high grade alloy. So if you're working with high temperatures, one of these two could be a possibility. And this is mainly used for aircraft industry. Here we use automobile and aircraft as well. Okay, so there's some specifications and what we need to understand the terminology here. So typically, the first thing that you have here, it just tells you what the diameter is. I'm going to go to the next chart and show you how it works. And then the second number that you're doing is the pitch, okay, the thread size, sorry. So this is diameter, the thread size, and all these letters just tell you this is unified series, this is fine, this is coarse, this is round root. When I say round root, I'm talking you know, you can have one side of the screw that looks like this, but if it is round, what we are saying is now it has rounded edges. Okay, so it's not completely. So here this is round. Okay, so the root is round. Here it cannot be round, but here it is. So that's what it really means. And each one of them has their own applications. So to better understand this is the nominal diameter, and this all come from tables. We're going to see this in the next table in a moment. And then this is the threads per inch. We're going to use the letter N for that. and this is the thread series. This is the total length of your fastener. So you have your fastener um, or your screw. So in this particular application or this example, this will be 1/4 inches. This will be 3¼ inches long, and 20 will be the number of threads that you have per inch. Okay, so threads per inch in this case is 20. This tells you the class fit, this is the material grade, and this is the bolt type. So it basically tells you what this part looks like. Okay, this is the most general case in the most general. So if you had something like this, right? And I told you this is 1/4 inch, so maybe 1/4 inch is somewhere over here. But let's suppose I want to use maybe this one right here, right? And I want to point out that you got this table is in your textbook. And then if you use this table in your textbook, you're going to see that you have two series. One is the coarse series, the other one is the fine series. Depending on the side that you are, it's going to give you different values, right? So if I say this is coarse, and then, so what if I told you this is 1/8 inches slash 40 UNC. So then if I gave you this, oh, this is right here. This is class 5, okay? So this is not class, sorry. This is the designated size. So this is actually screw number 5. And it says this is the major diameter. That's what it's giving you, the major diameter. And has 40, so it's 40 right here. And then this just gives you the tensile area and the minor diameter. We're going to use that. So it's only given in the table. Then now, what if I gave you the same thing, and I said, now this is 44 U and F. Okay, U and F. Oh, this is fine. So then you have to come on this side of the table, and then you say, hey, this is right here. So in this case, it still be number 5, or it would be this, but the properties are different. Okay. So if you're asking, how do they actually calculate it? What if I wanted to have the root diameter, the minor diameter, the pitch diameter? That's given by this equation, okay? And what's the value of the pitch? And this we will talk about that later as we continue our discussion. Okay, this is the unified series, but then you have the metric series. The metric series, this is the nominal diameter. This is your D. This is your pitch. Now it's not N, it gives you P. Remember, pitch is what goes from one crest to another crest. Thread is the number of threads that you have to hold over the length of your of the screw. Okay, this is the material class, and this is how the head bolt actually looks like. So if I was going to do something like this, for example, now you have, just watch, this is different. You also have a fine series, you have a coarse series, and that's it for this example. Okay, you want 12, this is inches, this is pitch is equal to 1.75. This is the tensile area. You also, if it's a fine series, then your pitch will be 1.25. So you just have to be careful in terms of you're working in a coarse series or you're working in a fine series. Typically, here you don't have that identified. It doesn't tell you if it's fine or not. But what you will do is, if you say 12, 1.25, you go to 12 and you go, oh, wait, I don't have this. Oh, well, I have it here, right? So then that's how you will know this is a fine series. So that's how these actually, this particular screws actually work. Okay, and this particular example, in this particular screw, this is easy to find because this you already know, and this is given by the pitch diameter, so just use this equation. Okay, and note that equations, give me a moment. Yes, the number is correct, but changes is only this one, 0.38. And by the way, this is table 8.1 and 8.2 of your textbook. So let's write this down. Um, this one would be 8.2. This one is 8.1, okay, of your textbook. So let's move on. You also have a AMC series. In the AMC series, what you have is Acme ASME series. What you have, and these are they're popular, especially when you're working in threaded and power transmitted applications. This is an example of ASME. So this is I'm sorry, ACME. And this one is squared ASME. So this is square, an example of squared. You can see how it looks like. So this is completely squared. And here, just remember D is equal to dm. And this is how all these configurations look like. So if I tell you this is typical, that tells you what your alpha actually is, your pitch angle, and tell you how to calculate all these dimensions. However, it's very convenient to use this table. This is not in your textbook, but I wanted to include this as an 8.3 from your notes. And that's how you will find, you can see that you got your pitch diameter. Pitch diameter is your dp is equal to dm. Your minor diameter is dr. So major diameter is d. And then this is tensile area that you will use for your analysis. So this is AT. This will be like the tensile area calculated here. You see this is the tensile area used for your calculations. That's what you will use. Um, and then this is the thrust per inch. This is N. This is equal to P. And how do you find one and the other? The relationship is P is actually equal to 1 over N, or N is equal to 1 over P. That's how we find those relationships between one and the other. Okay? So the mechanics of power screws, now that we understand more or less how the screws work, there are a couple of applications, and I just outline this. This is given in your notes. You may want to take a careful look at that, and just tells you what your thread angles typically are, and where do you use this. This is for low friction, this is a high friction. These are very difficult to manufacture, and the reason behind this is because of this guy right here. They're very difficult to get in there and remove that material. This is a lot easier. You just come with a cutter and just cut this out, and that's very easy to do. Then these are very so the strength of these are very good. This doesn't have very good strength, but it's very good for shear applications. Okay, so there are different applications. Now, when we are trying to study power screws, what you keep in mind here is the mechanics of power screws. You have a system like this, right? So this is a power screw that's actually is meant to hold all this load that's going up and down. You got this load here, okay, a big load W, and you want to make sure this screw is going to hold it. This is another type of screw. This is a gear, but it's another type of gears. Are kind of like screws, but they act differently, and they're meant to transfer power, not to hold power or load. Okay, and so one of the things that you want to do here is meant to, you got angular motion. So as I move this angularly, this moves up and down. Okay, so it transfers an angular motion to a linear motion. That's the real purpose of power screws. Okay, the power screws mechanics, this is how they really work. This right here is hard to see, but this is phi, this is psi, and this is called the helix angle. And this right here is hard to see. This is called lambda. This is called lead, the lead angle. And then basically what you want to see is this is probably resting upon something. Okay, this is resting on something. And then when that's resting on something, and then here you have the surface, right? And then you have all this load applied here. You see, you got this load applied here. And what this is doing is this is actually this is equally distributing your load on both sides, and that helps our analysis. That's how you get the analysis, okay? So this analysis here is thinking, let's go and take one piece right here and see what happens. And your pitch angle goes from one edge to another edge. You can do the crest, but crest is only good when it's actually pointed, right? When it's squared or ACME series, then you have to go from one edge to another. That's your pitch angle. And all the threads are going to have exactly the same pitch angles as well. Okay, so this is what it looks like. If you want to calculate what your lambda looks like here, that's given by this equation. So you can have your lead. Remember your lead again, this is n times p, where this tells you if it double start, triple starts, a single start. We did it at the beginning of this lecture. And this is your mean diameter. Okay. Then what you want to calculate in these problems is the force. That's one of the main goals of this. And the question can be a little bit complex and crazy. Just remember here that your tangent of lambda is actually equal to lead times dm. So if I take this and I plug this value inside there, that's how I come up with this expression here, okay? And the same thing here. This is by substituting this expression for lambda, tangent lambda, tangent lambda, tangent lambda. Okay, so you can do the whole expression. I am not going to do this derivation. This is your final answer. This is what you use. Or if you have the lead angle, you can use this. So use one or the other. And so when you do this, this is to rise. When you're rising something, you probably need a lot more force to rise. This is the force that you need to lower. That's why there's a minus sign, because you need less force to lower it. Okay, think about a jack, right? A power jack that you're lifting your car to change a tire. And you see, when you're getting started, it takes a lot more effort on your end to lift the jack than it takes you to lower the jack. Okay, so that's the rationale behind that. This number will be smaller than this one. Okay, so in other words, FL will always be smaller than FR. Okay, what we really care and do the analysis is the torque. This is the amount of torque that I need to apply to move it up and down. Okay, this is the color. This is the influence because of the color. And remember again, I want to keep emphasizing this is the same. And this right here, mu, this is the coefficient of friction in the problem. The coefficient of friction is given in your textbook, and I'm going to discuss that in a few minutes, where it comes from. So this is your final expression. This is the expression you will use. And just to point this out, your alpha, this is your lead angle, this is your thread angle, okay? Thread angle. If you remember this, so it will be, this will be alpha, okay? This is alpha. And so if you just do this, and this is 60 degrees, then your alpha will be 30, because alpha is half of that, okay? So so it will be alpha, 2 times alpha is 60, so alpha will be 30. I just want to point that out there, okay? So basically what you're saying is the color is this application right here. This is the color. The color doesn't necessarily always help. It reduces your, it actually works sometimes against you, but we will talk about those applications in a few minutes. When we do an example, we will see the effect of with and without the color. And the color has its purposes, but actually reduces the efficiency of your power screw. If you go to the table 8.5 and 8.6 of your textbook, you will see that you got different types of friction. This is the thread. So this is what is going to go. Uh, this is the friction for your thread. This is for the collar thrust friction. This is mu c. And you can see you're going to have different values. Okay, you're going to have a value when you're running, the value when you're starting. What happens is, if you think again the case of a power jack, you're going up and down your car to change the tire. I'm not sure if you're familiar, but you can see that when you're starting to go up, it's a lot more tougher. The same thing once you stop and you start now to go down at the beginning, you have to give it an extra push and then it keeps running, right? So as soon as you start, these are the starting values and these are the running values for which is way smaller, okay? Then you got two unique applications. One is when you want self-lock. Self-lock is the case of the power jack or the car jack, right? When you stop rotating this guy and you stop, you want this to lock itself. You want it to stay there. So the condition for locking is given by this expression, and if it's a square thread, so a power screw is given by this expression. Okay, depending on what you have, then you use those either this or use lambda. Uh, it's depending on what information you have available. Okay, and then the total torque to the torque turn to lower has to be positive. So that means that it will lock itself. Now, the case of overhaul, that's the only application I could find, an example I could possibly find, is this water flow system where basically it's rotating by itself. It's not requiring much torque. Actually, it's something like a negative torque, if you would. In that case, then this is the condition for overhaul is given by this expression. And it has its purposes and application, especially when you're working fatigue problems where you're going up and down. Then those conditions you may want to design something for overhaul, right? Because if you think you're going up and down, up and down, up and down, you never want this to go up and lock itself, come down and lock itself. So in that case, you may want to design that for overhauling. Okay. One last thing before we move to do an example is the screw efficiency. And the screw efficiency is given by this expression right here. This is total force applied in the total force this has to carry. And this is the torque to rise. Okay. This is the rise torque. Okay. So in the next example that we're going to do is we're going to better explain how this works and how to use all these expressions. Then that will be a lot more clear to you. Okay, this concludes the discussion on the theory of power screws.